Hello everyone. So today I will try to explain to you what is steam iron process and what is the methane-to-hydrogen project, and also, or mainly, how we use ChemApp to do this. Yeah. So firstly, the table of contents is as follow. I will start with brief introduction about steam iron process and our concept. Then the process modeling and how we modeled our process simulation, and also how we control the process. Then I will show you the process flow sheeting for both reduction and oxidation processes, and I only show the graphical user interface and the transient results for the reduction process, because doing both reduction and oxidation will be a lot of time. And at the end, I will summarize everything and give you a summary about what you're doing in the future. So firstly, as we know, hydrogen now is critical for the industrial decarbonization, especially here in Europe. But the question is, where will get the hydrogen? So the concept of steam iron process. So if we are in places where for example, in Africa, I don't know. So in Africa, we have renewable energy, and using electrolysis, we will be able to have hydrogen and oxygen. And the aim is to use, so if we have a reactor which is filled with iron material based, and then we will try to store the hydrogen thermochem in these batteries, if we can take the reactors as a chemical battery. So following this reduction reaction, we can so once we completely convert the oxides into hydrogen, we can say that our batteries now is charged. And the question will be is how we can transport it to Europe. So the idea is to have big ships or big platforms having on top these large reactors, and these reactors will be filled one time with the iron oxides, and on the ship the reduction process will be done. And once the reduction process is finished, the ships will be transferred to Europe, and in Europe we will do the reverse reaction. So the ships will go on deck, and then steam will be generated in Europe, and steam will be then injected into the chemical batteries. And once the iron is completely oxidized to iron oxide again, so the battery will be discharged, then the ship will be transferred back to Africa, and this will be iterated or be done several times and creating a cycle. And the goal now is to develop a large concept, a large energy efficient concept of steam iron process. And in order to do this, at the beginning we were thinking about, okay, so we need to be able to do several scenarios and examine several scenarios, do similar flow sheeting, user-defined flow sheets. And to do this, ChemApp for Python was the best option. So I will start with process modeling. So process modeling is actually based on linking these equilibrium reactors together with streams. And at the end, we form a user-defined unit operations. For example, if we take a look at this developed unit operation, this is a redox reactor, and this redox reactor operates at a constant volume, and it is assumed inside the reactor that we have a perfect mixing and no spatial gradients. And this equilibrium reactor can have several streams, several input-out stream, as already shown in the previous PowerPoints. And for example, we developed another customized unit operation, for example, called condenser, in order to dry out our process gas and separate, for example, hydrogen from steam, for example. And by combining, for example, several unit operations by streams, we can create at the end a big flow sheet. As can be seen here, we developed a user-defined unit operation, for example, redox reactor, condenser, heat exchanger, compressor / generator, evaporator, and liquid tanks. And the most important thing that this is done one time. So each unit operation here was like programmed one time, and at the end it is now a Python class where we and this Python class is only plug and play. So now I defined it one time. So yes, it needs to take a lot of time to develop this class, but at the end now I have a class where I just like plug and play, and that's so convenient. So now to the simulation itself. So we did a transient simulation for our process. How? Actually, by just connecting this unit operation together with the streams. So if we take a look, for example, at time step t, we assume that we know in the reactors or in the unit operations that we know the condensate phases and the gas phases. So we assume the system is in equilibrium. So at the next time step, we introduce our streams. So here it's written gas transfer because the redox reactor, the unit defined or for this unit operation, we assume we have only gas transfer. So that's why I said gas transfer. But actually, this step is like the mass and energy transport. So, for example, the first input stream will be like hydrogen or steam, depending on the process, reduction or oxidation. And we have an output stream, which will be transferred to the next unit operation. As an example here, the other redox module. And actually, we want it to be more realistic, and we want to control, so we want to control the pressure in the first reactor to be more realistic and to like simulate the gas flow from reactor to another. So what we did, we just implemented a BID controller algorithm. So this is a snippet from the code. And this algorithm was running in parallel to our simulations. And this BID controller was trying to regulate the resistance valve, this R valve value, which can be seen here in this equation. For example, here, the N dot out, or the stream out, is a function of the pressure difference between the two reactors, and the resistance of the valve is adjusted or controlled by the BID controller, and our bark is the resistance of the solid particle itself to be more realistic. The other issue is we need to bring heat to our reactors. So the idea is to use oxygen to oxidize, like to partially oxidize the hydrogen, and then we get energy to our reactors. And the idea was also, okay, we need to have a defined temperature, a constant temperature. So we also integrated BID controller, which regulated the amount of oxygen needed per time or per time step in order to have a desired temperature. So now we have a change in composition in our reactors or in our unit operations. So now the system is not in equilibrium anymore. So here comes ChemApp. We calculate equilibrium, and then we go to the next step. And this procedure is performed each time until the final state is reached. And now we have data, and with this data, we can simulate a transient process. So now this is the simple process flow sheet, the first one done for the reduction process. So we simply connected 5 reactors in series. And as I said, the reactors are temperature and pressure controlled. So here is the graphical user interface. So here comes Python now. So we can do graphical user interfaces, we can do visualization and so on. So this is the graphical user interface of the reduction process. And now here we can see like several things as a function of time. Yeah. And we can see the development as a function of time. And this is really helpful. So for example, the first one is the temperature in Kelvin versus time, or as a function of time. And then we have pressure. We have the oxygen needed per time in order to achieve a desired temperature, as can be seen here. It was around 700 degrees Celsius. And we can also compute or see the development of the oxidation degree per unit time. And oxidation degree here is number of moles of oxygen divided by number of moles of metals. And as you can see, it's really, really helpful. So if we deeply analyze or see, for example, only the temperature and the oxygen needed, so now we can see individually how much oxygen per time step each reactor needs in order to achieve the desired temperature. And as can be seen here, for the reduction process, all the reactors have to be heated in order to conduct the reaction. However, we can see that in this diagram that the subsequent reactors needs actually less oxygen than the previous reactors, and this is due to the energy transfer from the previous reactor. So actually making the process more easy for us to understand and visualize. Another graphical user interface, which I find really important, is the Bauer-Gresnet diagram. So this is a Bauer-Gresnet diagram is actually a phase diagram, but on the x-axis is the molar fraction. Here, in our case, molar fraction of H2O, and on the y-axis is the temperature. And here is the Bauer-Gresnet diagram for each reactor. So if we go and analyze deeply reactor 5, which actually the last reactor, which gives us insight about our process gas. So what is the composition of the gas we will have at the end of the process? So here we started in a spinel phase, and then with time we can see the development or the process path of the reactor. So actually we can know now the phase development or what happens actually inside the material. So at the end, with this information, we can know, okay, if the pellets will swell or will disintegrate, and so on and so forth. So actually, this is a really helpful diagram for us. And as can be seen here, or maybe better here. So this is the gas composition of the reactor 5. And as we can see here, the gas, the top gas of reactor 5 has still a lot of amount of hydrogen. Yeah. And this is not good. We want to increase the efficiency of our process. So that's why what about recirculation? So what about to recirculate this stream back again into our process? And also, as can be seen or from the previous diagram, also the top gas had also a higher temperature. So we thought about, okay, we want to recycle this stream, and also we want to recover the heat from this stream and use it to heat and use it to heat the new or the fresh hydrogen needed. So now the process flow sheet became a little bit more complex. So we integrated like compressors, several heat exchanger, and also condenser in order to separate the hydrogen here from the steam, and then we mix it again with the hydrogen fresh, and then we re-inject it again to our process. And with this heat recovery, we were able to reduce like about 47% of oxygen needed for the process, and this is actually a lot. So if we translated this to hydrogen consumption, it will be about 14%. Yeah, this is a lot. So now I will go fast regarding the oxidation process. So firstly, for the first scenario we developed for the oxidation process was this or had the same configuration as the reduction process, but we had an issue where we like in the subsequent reactors we had an overheating. So here we can see from the diagram that the target temperature was around 700 degrees Celsius again, and in the subsequent reactors we had relatively higher temperatures. Why? Because two things, oxidation reaction is exothermic, and also due to the transfer process from the previous reactors into the subsequent reactors, heat is transferred. So the reactors gets like a lot of heat that is not needed for the process. So we developed several scenarios, really. So this is the tense process flow sheet we developed. And that's why ChemApp for Python was also helpful, because we utilize the parallel processing and so on and so forth. So after a while, we were able to find a scenario where the gas transferred will be not 100% transferred into the subsequent reactors. However, it will be separated into different streams, and those streams will be also regulated with BID controllers. And as can be seen here in the down diagrams, so the left one is the base scenario, so with the normal configuration, and the second one is with the new configuration. And as we can see here, we did manage to do it. So here we had like the desired temperature we needed. So another important aspect regarding the oxidation process is the steam generation. So we need steam here in Europe. So the idea was, okay, to recover the heat again that we get from our process through implementing several heat exchanger and so on and so forth, and to implement evaporators, for example, for each reactor, to implement evaporator for each reactor, and this evaporator will be connected to a liquid tank, which will store the heated liquid we heated by the process gas. And also this evaporator, the user-defined evaporator in operation, has a controller which controls the amount of hot water needs to be taken from the liquid in order to achieve a steam at a desired temperature and pressure. And if the water is not enough, so okay, we will add some fuel to it. And unfortunately, I couldn't now like explain everything or introduce you all the results, because it will take a lot of time. But we did manage to do it, and was with explaining the several or with comparing the several scenarios we adapted, we will be able to assess our process, how it is energy efficient. So what is our energy? Is our process energy efficient, and so on and so forth. So to summarize everything again, the reduction and oxidation process were modeled independently as transient state process, and this was really helpful for us. And the models or the scenarios consider several aspects, for example, heat recovery, recirculation, steam generation, and so on and so forth. We implemented, or we would be able to define or have several process flow sheets by integrating our customized unit operations. And this allowed us to study and investigate several scenarios to optimize and reduce hydrogen consumption in the oxidation part. So now our goal is, so as I said, or maybe I didn't explain well, our redox reactor was one stage reactor, but now we are willing, or we doing it. So now we are doing the same scenarios, but with in stages redox reactors, and this will help us to add some kinetic constraints by, for example, by bypassing as already explained in the previous PowerPoints. And also we can analyze and investigate the, for example, the temperature development inside our reactor, the pressure development, the basis development inside our reactor. And that's it. Thank you for your attention, and feel free to ask me anything.